So let's get point 3 of 17.1. What we'll actually do is this will be really the last lecture, because we had the exam 3 was cancelled, so that would have that sort of gained us 2 lectures actually, and so I don't want to cover any more material. Then we'll just end with today's lecture. But I do want to say, a few more things about let me see. Maybe I can raise this a little bit. Refocus. A few more things about the Green's theorem, right? So if you remember what was Green's theorem, is that if I have the region D bounded by some curve C, then the integral around C of P dx plus Q dy is the integral around D of dq dx minus dp dy dA, right? And so now one of the things that we saw last time is that you can use this to compute the area, right? So we had the area of D was equal to the integral around C. Well, there's a couple of ways of doing it. First, let's do it this way. If we look at the dx part, we can write it as this, or we can write this integral, or maybe the average of the two. So this would be minus y dx plus x dy. That would also work, right? And so with this, we can also figure out a formula for, as I mentioned last time, for a polygon in space. So what we have is, if we have a polygon, right, then maybe it has sort of try to get them at these points, but so let's suppose that I have this polygon, and it might have a lot more, but let's suppose this is at 1. Let's do it 1, 2, 3. This would be at 5, 0, let's say, and this would be at 7, 4, and this guy would be at 2, 3, 4, and up by 2, so 6, right? And I claim you can compute the area by just you write down the coordinates 1, 3, 5, 0, 7, 4, 4, 6, and now we go back 1, 3. Okay. Now what we'll do is we'll multiply and add like this. So we'll have 1 times 0 plus 5 times 4 plus 7 times 6 plus 4 times 3. And then we'll subtract, I'll need another parentheses afterwards as well. We'll subtract, basically doing the thing in the reverse. So it's 3 times 5 plus 0 times 7 plus 4 times 4 plus 6 times 1. It's not quite the area, but 1/2 that is. All right. Now, why does this work? Well, this is actually precisely this version of this formula. And for each one of these, we get it's one of each one of these additions is one of these lines, right? So if we get, let's look at maybe the curve from here to here, right? And we're going like this. So the piece of the curve from here to here. Well, so this is the polygon P. This was the area of P, right? So this is the shoelace formula, right? And so let's compute. Let's just compute one, just so that we don't overdo it, right? So let's suppose that this line, this is we call it gamma. Why not, right? And so the integral over gamma of, well, I'm going to do 1/2, and then I'm going to do y dx plus x dy, right? Now, how is gamma parameterized? Let's call the parameterization R, why not? And we'll have, so x is supposed to go from 1 to 5, right? So we could write it as 1 plus 4t, right? And y is supposed to go from 3 to 0, right? So we could write it as 3 minus 3t, right? And where t is going from 0 to 1, right? So at 0 I get 1, 3. At 1 I get 5, 0. Okay, great. That's what this is, right? Let's compute the derivative. The derivative is 4 minus 3, right? So I have, this is 1/2, the integral from 0 to 1 of minus y. So minus, where is y? Y is this, right? So minus 3 minus 3t times dx, so 4 plus x, x is 1 plus 4t times dy was minus 3 dt, right? And this is equal to, let's write it over here. So I have so 1/2 out, and let's simplify this. Well, there should be a big parenthesis over here. We have 4 times minus 3 plus 1 times minus 3, right? Sorry, yeah, right. So we get 4 times minus 3 is minus 12 plus plus 1 times minus 3 is minus what would it be, 15, right? Then what about the, how many t's do I have? So I have, so this is minus minus, so plus 4 times 3, so I have 12t, and then I have minus 12t, right? So I have 0t, right? So dt, and you know, what is this? This is the same thing as 1/2 times 1 times 0, maybe you can't really see it, but it's coming from the t's, minus 3 times 5. It's this guy over here, right? If you compute it for all of them, you'd get precisely just the same formula. And if you compute it for a general 2 points, you'd get this formula over here. Let's not necessarily do that, but you can see that it's what I wanted to show you, that it really comes from Green's formula. Yeah, we get this funky way of computing the area of any polygon. It's very simple. You can it can be very, very complicated, and it's just this shoelace formula, right? Just plug in chug. It's very easy for a computer to do, right? For example. All right, let's look at another application of Green's formula, and that's you might have something, and this actually does come up quite a bit. So a simple vector field. Let's look at the vortex, right? We know that that's not a conservative vector field. So it's minus y, but it's an irrotational vector field. And these kind of vector fields actually do come up quite often. And let's suppose that C is some complicated curve that goes around the origin, right? And we want to figure out what is the integral of C f d. This is the way that we were writing it, right? Well, maybe it would be really, really tough to integrate, because parametrizing maybe a thing would be hard. But what we can do is we can easily parametrize the circle of radius 1. Let me call it C is taken. Let's call it C prime. I want to call it C a circle, right? Right. So I really want this, right? Now, what we could do is we could integrate it like this, right? In the opposite direction, right? Now I have a region in between, and I have this nicely oriented boundary. It's always the region is always on my left, so this is the correct orientation on this guy, right? And so if I call D the region in between, I get by Green's formula, we have that C plus prime of f dr is equal to the double integral over D of well, it's supposed to be, let me just write this, let me, this is dq, so I don't have to write it again. So dq dx minus dp dy. And if you do this, if you actually do the calculus, this is actually 0 in this case, right? And so what you'll get is 0. It's because it's an irrotational, f is an irrotational vector field. Well, that means that, well, this is C f dr plus f dr. Okay. Well, now this guy, that's really if we parameterize the circle from sort of one using sines and cosines. What we're going to do is I'm going to go the other direction. I'm going to go like this. I'm going to go counterclockwise and put a minus sign over here. All right, minus y is sorry, 2 pi over here, from 0 to 2 pi, right? So the angle goes from 0 to 2 pi. Minus sine t divided by cosine squared of t plus sine squared of t. Now dx and dx, if I have if I'm parametrizing by cosine t sine t as usual, right? Then dx is minus sine, right? And then I have x is cosine t divided by cosine squared of t plus sine squared of t, and the derivative of sine is cosine, so cosine of t, this whole thing dt, and you'll notice that this is 1, this is 1, this is sine, so minus sine t times minus sine t is just sine squared, then I have cosine squared, sine squared plus cosine squared, again 1, so this is just the integral, sorry, this is terrible, this is terrible, this is not equal, of course. What did I do over here? This is the integral of just c prime, right? I jumped ahead in my head. So this is right, 2 pi minus dt, so this is minus 2 pi. Well, if the integral of c prime is minus 2 pi, then for this to be 0, it must be that the integral over c is 2 pi. Alright? Now this is sort of a fairly typical application of this, as much more complicated. Because this is this kind of procedure is actually used quite a bit in application to compute various hard integrals by rewriting everything into, well, something like this, right? So it's not just a trick for one integral. This is actually used quite a bit. You can, if you have an irrotational vector field, then you have you can if it has sort of some hole, you know, the domain has some holes, you can just integrate around circles around holes, or around any path around holes, whichever path is easier. There's basically path independence, as long as I go around the right number of times to make this work out. All right, so that's one application. Let's switch notebooks. Let's look at one more thing with Green's theorem, and that's let's look at the divergence form of the theorem, because this is a place where it also gets applied quite often. So this is where you have I have a certain c, and I have a normal. Instead of integrating along a tangent, I'm integrating along a normal. And the way that the normal is done is the unit normal. It's this is which is the same as the x prime y prime, not magnitude, but That's we've seen that before, right? And so we have some d and some n. Now the divergence form of the theorem is maybe easier. We take if we have any vector field f, let's say f is again pq, right? And now we're integrating with respect to the normal, right? Then this guy, that's the integral over d of dp dx plus dq dy. It's sort of easier version over here. This is called this expression is usually called the divergence of f, right? And how does this work? Well, this works. It's still the same as Green's theorem, because what it really is. If you rewrite this, and if you notice that this just swaps the dx and the dy and introduces a negative sign, and it precisely introduces the negative sign on the dx. So if you rewrite that, you actually you would notice that this is this integral is this integral, and if this is this, then from here to here, this is just the regular Green's theorem. We have the x derivative of this guy, right, which is dp dx, and minus the y derivative of this guy. That's this, right? All right. So that's that's another version of the term. And what's where this is useful is actually figuring out how much stuff goes through a certain boundary, and again we can sort of use use Green's theorem to get an idea of basically by figuring out this expression in integral. It's especially useful if this is 0, right? This expression over here. Now let's sort of conclude with a formula, which is very useful about the Laplace operator that we've seen before. So if I have a function phi, right, then the Laplace operator of phi, I don't know if I've written as delta, sometimes it's written, I never know which way I've written it before. In my notes I have the delta, but I sort of vaguely remember that I wrote it like this. But in any case, it's this guy, and in modern physics, you keep talking about the Laplace operator all the time, and the Green's theorem tells you something about the Laplace operator. Those actually, if people say Green's theorem, sometimes they mean this formula. So the formula that we're going to give. This is such a useful formula, and it's this. If I take the normal derivative of phi and I integrate that over the boundary. Well, what is this? I mean, this is the normal derivative. That's the directional derivative along n, right? So what is this? This is the integral over c of the gradient of phi dot n. That's really just what the definition of this. Okay, now you apply this version of the Greenstream, the divergence version, and notice that the gradient of phi is the x derivative of phi and the y derivative of phi, right? And so if I apply this, then this is my p and this is my q, right? So I will have I will take this. I will take the x derivative and I will apply the x derivative again, right? So I will have the second derivative in terms of x, and I will add to it, take the y derivative, take the y derivative again. So the second y derivative. Well, this is just the Laplacian of phi. All right. So what this says is that if I look at how much stuff is leaving my region, right, it's equal precisely to the integral of the Laplacian of f. If I'm thinking of stuff leaving my region as following the gradient of phi, right? So phi is some potential function of something, right? Some vector field, let's say, right? And I look at how stuff is leaving. Well, that can be given by the Laplacian. Now there are special sorts of functions. So these are called harmonic functions. Those are the ones where the Laplacian is 0, and these are, for example, the steady state heat distribution, or maybe the potential for a charge, in the region where there's no charges, so in the region between charges. In an electric field, this comes up quite often, these kind of functions, and they have lots of wonderful properties. So one of the things that follows from this formula is that for a harmonic function, if I look at the this boundary integral, then it's 0, right? And it sort of tells you this is if, for example, if it's steady state heat, right? Well, this is how much heat is this is how heat is moving through your substance, through your object. I suppose we're in 2 dimensions, so it's in a plate or maybe cross section of something, and this is saying that for in steady state, the amount of heat leaving a region is the same as the amount of heat entering, right? Well, that's precisely what you expect for steady state heat, right? Because the heat is will still be moving as the temperature is not changing, right? All right, so let's not do any more. Let's sort of leave it here. Just wanted to sort of give you an idea that Green's theorem has lots and lots of very useful applications beyond just trying to compute some integrals. That would be a very, very weak application of Green's theorem. It wouldn't be as important if it was just about computing a bunch of integrals, right? I mean, computing integrals, doing some specific computations. I mean, that's something computers can do, right? That's not a the point is to understand what we are computing, and this Green's theorem tells us quite a bit about physics and about how things work, And so that's a much more important application of it than some specific computations, right? All right, so that's it for Green's term.